Hi everybody. So we're going to try video recording the pendulum experiment you would have been doing over 2 weeks if we were having Physics 120 live and in person. I want to give a special shout out to Jill Ackerman, our department administrative assistant, who's graciously helping me video record this. So in our first video, what we're going to do is we're going to talk through the modifications to the measurement circuit you've been working with that you'll need in order to measure the period of a swinging pendulum. Hello everybody. So here is the circuit that you're going to be using for the pendulum experiment. It's basically the same circuit that you've been working with all semester long and you used in the linearly accelerated motion lab, just with some added flip-flops. So let me walk you through what we have here. Okay, so over here, this is the signal from my phototransistor. Here in black, you can see how that's tied to my 22K resistor to ground. So that leg of the resistor is over here. I've got this purple jumper going in here to my Schmidt-Trigger inverter. The output of my Schmidt-Trigger inverter is this green wire here. I'm also monitoring that via this green wire on logic indicator number 1. Now, the new element in this circuit is the fact that we need to have 2 divide by 2 flip-flop circuits here. So the output of my Schmidt-Trigger inverter is going to this chip. This is my 74LS74 dual flip-flop. So let's walk through those connections. So one thing we want to do this time is we want to be able to have clear star for both flip-flops controllable. So clear star for flip-flop number 1 is pin 1 on this chip. So I've tied pin 1 via this brown wire to switch logic switch S1 down here. Now with going from the same connection, I've got this other brown wire going from this pin number 1 over to pin 13, which is clear star for flip-flop number 2. This is our classic flip-flop biting its tail divide by 2 circuit. So here we have Q star, which is pin number 6, tied to data, which is pin 2, so that there's that connection there. We want set star tied high, so it's active low, remember, so tying set star high means that we don't assert it. That's done over here on pin 4 for flip-flop number 1. And now we take the output Q of flip-flop 1, so that's this yellow wire here coming off of pin 5, and we tie that to clock, which is pin 11 for flip-flop number 2. That's going here at pin 11. Now, as I mentioned, we have clear star already tied to switch S1 for both of my flip-flops. For flip-flop number 2, we also have in orange here from pin 8Q star to D at pin 12. Once again, we have set star tied high here at pin 10. And then finally, the output of the second flip-flop is Q, that's going to be pin 9. I've got that here from this green wire over to my AND gate. I'm also going to monitor that via this orange wire on logic indicator number 2. Okay. So that's all the connections for our 2 cascaded divide by 2 circuits. So the rest of this is familiar. I have now my AND gate here. That's tied to my BNC connector here, which I'm going to drive from my clock. And then the rest of this is so we've got the output of my AND gate driving my 3 cascaded counters here, and then driving my display circuit, just like you've been working with. Okay, so let's see if this circuit does what we think it should. So right now I have my photo gate set up, which it's off the camera now, but let me turn this on. So right now we have light that's shining into the photo gate. So the photo gate is not blocked. So as we expect, the output of our Schmidt trigger inverter here on logic indicator 1 is low. If I reach around with my finger and I block my photo gate now, you can see that my Schmidt trigger inverter has gone high. So I'll do that again. So block, unblock. So that's working as we expect. Now you'll notice that nothing yet has happened with the output of our 2 divide by 2s. And that's because here S1 I still have low, so I have asserted clear star. So only until I'll have to first slide this switch up, and now the flip-flops will start doing their thing. So let's watch what happens when I go through a sequence of blocking and unblocking my photo gate. So let's do a block now. So I've blocked it, I'm still blocking it. We have our Schmidt trigger is high. Our output of our 2 cascaded divide by 2s is high. So now I've unblocked it. So that's sort of the pendulum swinging one way. Now let's do block number 2. And I'm going to block it now and unblock it. Notice that the output here at LED 2 has remained high. Now what we want is that if I block this again, this drops back low. So let's see what happens. So coming in for block number 3, again, it's still blocked. Notice that our 2 divide by 2s has dropped low. And now I've unblocked it again. And so both of those outputs are low. And now I can slide S1 back to low to disable further counting. So now that we've seen how the circuit does do what we expect it to do, we're next going to look at the pendulum setup and do a plausibility check to convince ourselves that the entire measurement setup is working the way we expect. Hi everybody. So here's our pendulum setup. So what we've got here is I have a metal ball tied to a piece of string. We've got these big stands here. I've tied the top of the metal string to this crossbar on top. And if I let this thing go, it's free to swing. Now you can see that I've rigged up the photo gate here. So here's our LED light pen, here's our photo transistor. And you can see that the way the pendulum is set up, when it swings through the bottom, it is set up to block light from going from the LED to the photo transistor. Let me actually turn this on. And I think you could even maybe see the light getting blocked over there. So I'll turn that off for now. And so you can just see how I've got this mounted over here, and then the photo transistor is going to the measurement circuit as we described earlier. Okay, so what we've got set up here is we've got, so I really hate those BK precision function generators you've been using. I think they're based on some analog oscillator that has really dreadful stability. So I've actually taken one of the nicer Rigol digital arbitrary waveform generators out of the closet. Now it might look like there's nothing connected to the instrument, actually the TTL output we want to use is actually on the back panel, so that's why you don't see anything hooked up to the front of this. And I've got an oscilloscope here because I like looking at things on oscilloscopes. So right now, I know you probably can't read the display here, but I have the signal set at 100 hertz. And if we look at the scope, we can just confirm that that's what's happening. So on the horizontal scale, I have 5 milliseconds per division. So you can see that one period of the clock signal is 2 boxes, so that's 10 milliseconds, which is in fact what we would expect for a 100 hertz signal. Vertically, we're at 5 volts per division, and let me just show you that if I twiddle this down here, we in fact have a signal going up 1 box, so we do have a healthy TTL signal. Okay, so that clock signal is getting fed over here, and let's see what happens. So right now, I've just turned my measuring circuit on. The pendulum is right now over here. It's hanging and blocking the photo gate. So we in fact have a high on indicator 1. But let's just first see that this counts when we expect it to. So when we're doing this experiment, when we set the pendulum swinging, we probably want to let it swing through 1 or 2 cycles to let any transients die out. And then when we want to start counting, I'm going to slide the switch S1 up high so that I will stop asserting clear star on my 2 flip-flops, and hopefully we'll see the counter start to count. Okay, so let's give this a go. I'm going to come over here. I'm going to pull my pendulum back and try to do it straight. And we have swinging now. All right, so the next time, I'm going to get ready to slide this up. And now. All right, and I've turned it off. And we see that this has in fact counted. The counter has in fact counted. Let's just do that one more time. I'll clear the counter by pressing button 1. We'll get ready to slide switch S1 and measure a period. And now. And up, and once again, we see that the counter has counted. Okay, so now that we've seen that our timer circuit does what we think it should be doing, and we've looked at our pendulum setup, we should just do a plausibility check to make sure that our timer is giving results that we expect. So in order to do a plausibility check here, what I'm going to do is I'm going to use our timer to measure the period of our pendulum, and then I'm going to compare that to a quick and dirty measurement with the stopwatch on my cell phone. Okay, but first let's take a look at our setup over here. Just to give us a little more precision, I want to turn the frequency on this function generator up. It's currently at 100 hertz. If I come down here, and I set that to 1000 hertz, now it's reading 1 kilohertz. You can see here on the oscilloscope that the period of our clock signal in yellow is now way shorter. Let me twiddle with the horizontal scale. And now we're at 1 millisecond per division, and we see in fact that the clock has a period of 1 box, 1 millisecond, as we would expect. Okay, so let's give this timer a go. So I've cleared our timer here, our counters here. I've got now switch S1 at 0, so that is in fact, so it's not counting. Okay. So let's try getting this pendulum swinging. So I've gotten my timer, my counters are cleared, my clear is still asserted, so nothing's happening yet. I'm going to try to get this pendulum swinging. I'll pull it back and to a small angle and try to release it straight, more or less. All right, so let's try to catch 1 full cycle of this. So I'll slide the switch up now, so 1, and that's 1 full cycle. All right. So, looking, you can see that there's a number here. I'm going to grab my hex reading guide here. So the hex number that we're reading right now on our counter is 6, 7, and then this is sideways C, so that's hex B. So repeat, that's 6, 7, B. All right, let's check as well that that we're getting 1 period with our stopwatch. So I'm going to set this up. I'm just going to use the fact that this is still swinging, and I'm going to try to catch from the ends of the motion because that's easier. So I'm going to, I'll say now, and now when I'm starting and stopping. And now. Now. Okay, so having done that with my stopwatch, I've measured 1.63 seconds for 1 period of this pendulum. So what I would like you to do now is to think about this and see if a reading of hex 6, 7, 11 on our timer with a clock frequency of 1 kilohertz is consistent with the time I measured by stopwatch of 1.63 seconds.